Welcome to Unit 4 of Learning the Course Design and Analysis of Algorithms. We already completed 3 units of syllabus in this course. In those 3 units, in the first unit, we explained the introductory concepts, that is the basic concepts related to the subject, design and analysis of algorithms such as algorithm, pseudocode, asymptotic notations, performance analysis, disjoint set operations, connected and biconnected components, etc. Now, from second unit onwards, we started explaining algorithm design techniques. In second unit, we explained 2 algorithm design techniques. One is divide and conquer technique and other is greedy method. In third unit, we discussed about another algorithm design technique, which is nothing but dynamic programming. Now, in fourth unit, we are going to see another algorithm design technique, which is nothing but backtracking. Backtracking, an algorithm design technique. The main objectives of this unit are learning the general method of backtracking algorithm design strategy, applying backtracking strategy in developing algorithms to solve various applications, analyzing those algorithms for their time and space complexities. Coming to the learning outcomes of this session, by listening this unit, one can understand backtracking algorithm design strategy and solve applications by developing algorithms in backtracking strategy and analyze the developed algorithms for their performance. Coming to the syllabus of this unit entirely covered in 5 sessions. In the first session, we are going to explain about the general method of backtracking. In the second session, we are from second session to fifth session, we are going to see various applications which are solved using backtracking method. The first application, which is explained in session 2, which is nothing but n-queens problem. In session 3, we are going to discuss about another application, sum of subsets problem. In session 4, we are going to discuss about Hamiltonian cycles. In fifth session, we are going to discuss about graph coloring problem. Welcome to session 1 of Unit 4 in learning the course Design and Analysis of Algorithms. In this session, we are going to learn about the general method of backtracking algorithm design technique. The main objectives of this session are to learn the general method of backtracking. The learning outcomes of this session are, by listening this session, one can understand the general method of backtracking, able to follow backtracking strategy to develop algorithms for solving various applications. The topics that we are going to discuss in this session are the general method of backtracking, recursive backtracking, iterative backtracking, and state space tree. That is the basic concepts related to the backtracking, which are nothing but state space tree and some constraints, explicit constraints, implicit constraints, etc. Some basic concepts are there. We are going to discuss about all those basic concepts. Now, coming to the general method of backtracking. Now, what is backtracking process? Backtracking is a process where steps are taken towards the final solution, where we are going to take the steps to get the final solution for a given problem. If these steps do not lead to a solution, some or all of them may have to be retraced and the relevant details discarded. So here, what is the backtracking method? We are going to move step by step to get the final solution. If any step in this step-by-step process, if any step not lead to a solution, some or all of those steps are to be retraced. That is nothing but all are to be backtracked. That is, we are neglecting all those steps that we taken. That is, we discarding all the steps that we taken. We are moving backwards. And from the first step onwards, or from the where we move towards back. So whether we move to the first step or we move to the second step or we move to the third step. That is, for example, the first step I taken, we moved somewhat, I get some solution. Here second step I moved, I get some solution. I move to the third step. But here, if I not move towards the solution. So if the path deviates from the solution, in this case, we need to backtrack the process. Where we are backtracking? Suppose if I backtracked here, if I found another way to get the solution, I can follow that one. So if I'm not finding any way to get the solution from this step, I need to backtrack one more step back. So this backtracking continues till the root node. So this entire process, the entire process of backtracking, that is the step-by-step process of backtracking, is represented by using a tree structure. In that tree, from terminal node to root node, we can backtrack the process. So from where we are getting the solution, till that node we can backtrack. Okay, now in these circumstances, it is often necessary to search through a large number of possible situations in search of feasible solutions. I already said you that for getting the feasible solutions or for getting the optimal solution for the given application, we need to search for a large space which is represented or which is organized as a tree structure. This is a very useful technique. The backtracking is a very useful technique for optimizing search under some constraints. That is, every problem is having its own constraints. So based on those constraints, we need to get the optimal solution. So here, the searching process of the tree, here the solution is represented as a tree-like structure. The solution is represented as a tree-like structure. The searching for the solution of this tree can be optimized by considering some constraints. Now, we can express the desired solution as an n-tuple. That is, we can express the desired solution as an array, a small array we can express. That is x1, x2, so on, xn like that. So what is that x1, x2, x3, so on, xn means the input values which are present in the set S, a finite set S. Right. Now here you can see a small example of backtracking process. Here I represented the nodes with different colors. The green node which represents the starting point. Here green node which represents the starting point, and these are the intermediate nodes. These nodes are the intermediate nodes, and red are infeasible solutions. All these red nodes indicates infeasible solutions, and this indicates the solution. The dark green node which indicates the solution. Now what is this process? Let us see. When the algorithm propagates to an end to check if it is a solution or not. When the algorithm propagates to the end of the tree to check whether that path gives the proper solution, feasible solution or not. If it is, then it returns that solution. Suppose, for example, we are propagating in this direction. If it is giving suitable solution, we can return the solution. Here we can return the solution. If it is not giving the suitable solution, we backtrack the process. We move to this node. From this node, is there any alternative path if we check? If there is no alternative path, one more step we backtrack. And we find the alternative path here. We moved here and we moved here. We moved here. Here we did not find the answer. So we backtracked the process. We moved here. We did not find the solution. Again we backtracked the process. And we followed in this way. And we get the solution here. So I hope you all understood. First, we came in this path. Here I get the partial solution. I come here. But for coming here, I did not get the solution. This not leads to partial solution. So that's why one step I moving backward. I go for searching an alternative solution from this step. If I find, I go in that path. If I did not find, one more step I backtrack the process. From there, I go for another alternative. And here this is the partial solution. And I go for this path. Here I am not getting any solution. So I backtrack the process. Here I checked for alternative. Since this is the partial solution, from this partial solution, is there any alternative for getting the complete solution? I go for here, but here also I am not getting any solution. So I backtracked the process. So there is no alternative, another alternative. So again I backtracked the process. Here I searched for another alternative. This is the partial solution and I moved here. This gives the complete solution. So here, since if you get any partial solution, from that partial solution, if you are not moving towards the complete solution, in that case, we are reaching towards or we are backtracking the process. So we are moving towards back. So that's why the name backtracking for this algorithm design technique. We are calling this algorithm design technique as backtracking. Why we are calling that as backtracking means we are moving towards back. So that's why we are calling this method as backtracking method. So coming to the algorithms of backtracking, we can represent the backtracking algorithms in two ways. One is recursive algorithm and other is iterative algorithm. Now first I am going to explain the recursive backtracking algorithm. That is, this gives the control abstraction for recursive backtracking procedure. Let us see that procedure. Algorithm backtrack of K describes a backtracking process using recursion. This algorithm describes the backtracking process using recursion. X1 to n is input vector invoked by backtrack of 1. So initially here this is the input vector. X1 to n is the input vector. Now in that input vector we are invoking the process with 1, backtrack of 1. Now for each xk in x1 to n, first we are taking one x value from x1 to n. If backtrack of x1, x2, so on, xk is true. If backtrack of x1, x2, x3, so on, xk is true, if it is true, and if it is a path to answer node. So, what the value we considered from x? Here, x is the input vector which contains n elements. Out of those n elements, we are selecting one element which is present at position k. We are considering one element from x. That element is nothing but xk. Now, from starting to xk, from starting element to xk, if this path, if this backtrack path is true, if all those values are true, and if this is a path to answer node, if this leads to partial solution, path to answer node means if it leads to partial solution, in that case, we are going to write x of 1 to k, and if k less than n, backtracking of k plus 1 I call for selecting the next element in the input vector. First we selected kth element. Now if k less than n, more elements are there, some more elements are there in the input vector. To select the next element, we call the backtracking of k plus 1. Right. This is the recursive backtracking procedure. Now coming to iterative backtracking procedure. So the same is explained in the iterative manner. What we explained in the recursive manner, the same is explained in the iterative manner. Here x1 to n is the input vector. Initially we are taking k is equal to 1. In the earlier process we represented, we start the process with the backtrack of 1. The same here I represented with k is equal to 1. While k not equal to 0, if untried xk in t of x1, x2, so on, xk minus 1 and bk of x1, so on, xk is true. Now we are considering one untried value from the given input vector. So given input vector, already x1, x2, so on, xk minus 1 I selected. Now I selected xk. So which is not equal to all these things. Here xk is not equal to x1, xk is not equal to x2, xk is not equal to x minus 1. Like that, an untried xk value I taken, and if backtracking of x1 to xk is true, and if this is an path to answer node, that is if it gives a partial solution. Now we write x of 1 to k and k is equal to k plus 1 considering the next value. Else, so if it is not leads to partial solution, we backtrack the process by taking k value as minus 1. That is one more step we are moving back by decrementing the k value. Okay, so this gives the iterative backtrack process. Now we are going to see various basic definitions related to backtracking process. One of those definitions, first one is state space tree. What is state space tree? A state space tree is a tree constructed from all the possible states of the problem as nodes connected via state transitions from some initial state as root to some terminal state as leaf. That is, the state space tree starts at root node, state space tree starts at root node and it moves towards getting the solutions, and it ends at some leaf nodes. So here these are the leaf nodes. All these intermediate nodes, all these indicates the intermediate nodes which represents partial solutions, Now, let us see once again the state space tree. What is state space tree? A state space tree is a tree constructed from all of the possible states. With the all possible states, we are constructing the state space tree of the problem as nodes. So here all these are the nodes which represents all possible states connected via state transitions from initial state to the that is root to the final state leaf. So connected here all these are the transitions from one state to another state. From root node to this state the transitions. From this level 1 state to level 2 state and from level 2 state to final state, that is terminal state. So all those are the transitions. Okay, at final state we can represent the solution. Okay, that is, suppose if it represents the solution, all this path entirely is considered as the solution path. Suppose for example, if this represents the solution, all this path entirely is considered as the solution path. Okay, so next, promising and non-promising nodes. What are the promising node and what is non-promising node in case of a state space tree? A state space tree contains number of nodes, reef nodes, root node, leaf node and intermediate nodes. Out of all those nodes, what becomes the promising nodes and what becomes the non-promising nodes? Let us see. A node in state space tree is said to be promising if it corresponds to a partially constructed solution that may still lead to complete solution. Suppose I constructed a state space tree like this. If I constructed a state space tree like this, now here this node is promising node. Root node always becomes the promising node. Now from root node, first I constructed this node. If this node leads to partial solution, this node leads to partial solution, and if I proceed from this node, if it gives a complete solution, then we can call this node as a promising node. This node as a promising node. Now, if I continue this path, if I get solution here, so this is the root node, this is the solution node, and this is the promising node. Suppose for example, from this, if I came here, till this it gives the partial solution, but if I continue from that node, it not gives the solution. If it not gives the solution, then it becomes a non-promising node. As I hope you all understood what is promising node, what is non-promising node. A node which indicates a partial solution, by continuing from that node, if it leads to complete solution, that type of node is called as promising node. Root node always becomes a promising node, right? Next one, state space tree. How to construct a state space tree? Now, a state space tree for backtracking application can be constructed either in BFS or in DFS. What is BFS? BFS is breadth first search. That is breadth-wise construction. That is, we construct first this one. From here, we construct these two nodes. From there, we construct these two these nodes like this. If you move in breadthwise, this is called as breadth first search. Depth first search means first we construct this node, from here we construct this node, from here we construct this node, from here we construct this node, and from here we construct this node. 6, 7. If we move like this, that is, we move towards the depth of the tree. This indicates depth first search. We can construct either BFS way or in DFS way. Both the ways we can use. Based on application, we select which way is suitable to solve that particular application. Now, if the current node is promising, its child is generated by adding the remaining options for getting the next component of the solution. And the process moves to the child. That is, if I found that this node is promising, if this node is promising node, that is, it gives a partial solution. Okay, promising, then its child is generated. By adding the remaining options of the input. And this process is continued till to its child. Suppose if it is also promising, its child will be generated. If it is also promising, its child will be generated. The process continues till you get the solution. So if there any non-promising node is occurred, the process backtracks it through previous node. From there, if you found any alternative path, we continue the path. If we not found any alternative path, again one more level we go for backtracking. The same I explained here. Let us see. If the current node turns out to be non-promising, if the current node is promising, we generate its child. If the current node turns out to be non-promising, then the process backtracks to the node's parent. If it is non-promising, we backtrack the process. That is, if it is non-promising means we cannot get a solution from that node. In that case, we backtrack the process to the node's parent and consider the next possible option. Okay, if there is no such option, from its parent also, there is no such option. It then backtracks one more level up the tree and so on. We can backtrack till root node. Now, when the backtracking algorithm reaches a complete solution, it continues searching for other possible solutions. So, if you get one solution for the one application may have number of solutions. Okay, after getting one solution, the process goes to find the next solution. Okay, so that is all the solutions which are present for that particular application can be obtained by using backtracking. All the solutions can be found. Right, this entirely explains the construction of state space tree. Now, we are going to see another two more basic concepts related to backtracking. Those are nothing but constraints. Here we have mainly two types of constraints. One are implicit constraints and other are explicit constraints. What about explicit constraints? Explicit constraints are rules that restrict each xi to take on values only from a given set. Okay, at every stage we are taking the input values. First, at root node we are considering one input value. At first level node, we are considering one input value. At second level node, we are considering another input value. Now, selection of input values, selection of each xi should be done from the given set. That is monitored by the explicit constraints. Okay, now explicit constraints are depend on a particular instance I of problem being solved. So, which instance we are solving? Based on that instance, the explicit constraints may be deferred. Now, all tuples that satisfy the explicit constraints define a possible solution space for I. All the tuples which are satisfying the explicit constraints are only considered into the solution. Now, for example, xi greater than or equal to 0 are all non-negative in real numbers. That is, our process or our application has to select only non-negative real numbers. If you try to select other than a non-negative real number, the explicit constraint should not be held. Every problem should hold both implicit constraints as well as explicit constraints. If explicit constraint is not hold means we cannot get the solution for that problem. Okay, so implicit constraints. What are the implicit constraints? Implicit constraints are the rules that determine which of the tuples in the solution space of I satisfy the criterion function. Now, by the explicit constraints, we are selecting one option or one value from the input. Whether that value is satisfying the criterion function or not, that is to be decided by implicit constraints. Whether that particular input we selected leads to optimal solution or not. Whether it leads to optimal solution or not can be decided by implicit constraints. The selection of xi can be done by the explicit constraint. Selected xi leads to solution or not is decided by implicit constraints. So those are the both explicit and implicit constraints. I hope you all understood the general method of backtracking. Now I am going to summarize the concepts what we explained in this session. In this session, we seen what is the backtracking general method, what about the iterative backtracking method and the recursive backtracking method, and also we explained some basic concepts related to the backtracking method, which are nothing but state space tree, how to construct a state space tree, and what are the promising and non-promising nodes, and also we seen the two types of constraints, which are nothing but implicit constraints and explicit constraints. To assess yourself, here I given some questions. Please answer these questions. The first question is, backtracking algorithm is implemented by constructing a tree of choices called as option A, state space tree, option B, state chart tree, option C, node tree, option D, backtracking tree. The next question is, what happens when the backtracking algorithm reaches a complete solution? Option A, it backtracks to the root. Option B, it continues searching for other possible solutions. Option C, it traverses from a different route. Option D, recursively traverses through the same route. The next question is, a node is said to be dash if it has a possibility of reaching a complete solution. Option A, non-promising. Option B, promising. Option C, succeeding. Option D, preceding. The next question is, write a brief note on general method of backtracking algorithm design technique, including its control abstractions, which are recursive backtracking and iterative backtracking. In preparing this presentation, I used the digital content from various public sources. This is used only for educational purpose and not for the commercial purposes. Thank you for listening the session.